Good morning, everyone. How are y'all today? Excellent. Good to hear. Oh, I don't believe I posted the last lecture on the YouTube. My apologies. I will do that after class today. But yeah, if you didn't know already, the lectures are in cloud recordings on the Zoom tab. You should be able to find them if I forget to post them to YouTube. So yeah, my apologies though. Okay. So no, it's I mean, treat it like a normal exam. Obviously, we have, I mean, there's no proctor, but treat it like a normal exam, right? You should be able to do this, close notes, etc. But yeah. What? Oh, what happened last semester in 141? Oh, gotcha. Okay. Yeah. So it'll just be like any other exam, close notes, etc. Except it's not being proctored, but that's all I will say on that. So no, I decided not to do a quiz this week because because of the exam next week, I pushed forward a lot of the assignments for this week, and I figured I think this is when a lot of people start having exams also anyways coming up. So you're probably all plenty busy, and I would rather you finish the homework and do the practice exams. So they're gonna start next week. And I know I've said that like 3 weeks in a row. It's true this time. So the exam is generally, so there could be the occasional multiple choice question, but those will be the exception rather than the rule. So you're not actually gonna like type anything for the most part into the exam itself. What you're gonna do is you're gonna write down your work. You're gonna upload it as a single PDF. And then that's what we're grading. So it's like a normal exam, right? You're writing all your work down, circling your answer, and that's the thing we're grading. But yeah, you're going to upload that after the exam. And I'll talk more about this as the exam approaches. So we'll have a review day on Monday during class, and I'll go more over this. I also need to see exactly all the finer details because since we have a new course coordinator this semester, it's not going to be exactly how it has been the past few semesters. So I need to make sure I'm also not giving you bad information. But we'll talk more about that. Where do you find the practice exams? Let me make sure they are still up. If you Google Math 230 Penn State, you can find the course webpage. Yeah, And on there, there's a sample exams tab. And so these are still sample exams from the previous semesters. So that was when we had twice as many exams. So you want to go through the sample exams for exam 1 and exam 2 for this exam, because we covered half as much material per exam last semester. Than this one. There we go. Okay, yeah. So yeah, the Math 230 website, just Google Math 230 PSU, it'll be the top hit, and find sample exams. And you'll wanna go through the samples from exams 1 and 2. Other than the notes and the practice exams, if you can get through all of the practice exams, which I would suggest you try to do, that is by far going to be the best way to study, because that'll give you a good idea of the kind of material you're going to see on the exam. I would say no. I wouldn't go out of my way to do anything other than those, and those will probably keep you busy for a while. So yeah, I would, by far the best thing you could do is work on the practice exams, I would say. Yeah. Okay. Yeah. All right. So, is there an answer key for the practice exams? Yes, there should be. I believe they all have. Let me check again. Okay, so for the first ones, they don't seem to have them. I'll see if I can get those. For exams 1, practice exams, for the first one, they don't have them, but for the second, they do. And from then on, they seem to. I'll see if I can get those. Yeah. But yeah, it doesn't appear to be so for exam 1. Alrighty. So today we're going to look at section 13.3, chapter 13.3, which is over arc length and speed. Okay. So suppose you have some space curve and it is parameterized by a vector function r of t, which is just going to be x of t, y of t, z of t. And suppose t goes from a to b. Okay, so that's our space curve C. And since we allow t to go from time A to time B, this is going to be a finite length segment of this space curve. So remember, parameterization of a curve just means you have a vector function where if you start at the origin, the tip is going to trace out your space curve, and it's going to give you position on the curve at time t. So suppose we start here at this end at time A, and we are here at this end at time B, and we allow t to go from A to B. So in this case, we'd be traveling in this direction along the curve. Okay, so we have the space curve. So we can talk about the length of the curve. So we can calculate the arc length of the curve in the following way. So the arc length is just, if you take this and you straighten it out and you look at the length, if you look at the distance you've traveled, so think of yourself as being a particle traveling along the curve. If you go from time A to time B, how far have you traveled? That is the arc length. So the arc length is, we like to call it S. Not sure why. I'm sure it's something German or something, but so the arc length is going to be the integral from time A to time B of the magnitude of r prime of t. I will talk in a second about an easier way to remember, or think about what this is saying, because the magnitude of r prime t is very important, as we'll see in just a second. But if you write this all out, that's kind of the shorthand. If you write this all out, remember the magnitude. So r of t is x of t, y of t, z of t. R prime of t, you take derivative component by component, so that x prime of t, y prime of t, z prime of t. And the magnitude is just the sum of the components squared. You take the square root. So that's the square root of x prime of t squared plus y prime of t squared plus z prime of t squared, square root of all that dt. Obviously, this is going to be the easier guy to remember, just the magnitude r prime of t. But that is how we calculate the arc length. The integral of magnitude r prime t from time A to B. Okay. So for example, really we could easily give you a parameterization of a curve for which actually calculating this integral would be impossible to do by the methods you know from 140 and 141. But we're always going to give you, we're not going to give you any of those. So really, there are going to be a couple things that are going to happen, right? So this will exemplify like one of them. So suppose you have a curve parameterized by the following. So r of t is 1/3 t cubed, t squared, 2t, and t goes from 0 to 2. So let's find the arc length. Okay. So to find the arc length, we need to integrate the magnitude of r prime of t. So let's calculate that. R prime of t. So r of t, 1/3 t cubed, t squared, 2t. R prime of t, we take the derivative of each component. So we get derivative of 1/3 t cubed is going to be 3 times 1/3 t squared, which is just t squared. T squared is going to become 2t when we take the derivative, and 2t is going to become 2. So we take the magnitude, we square each component, add them up, and take the square root. So t squared is t to the 4. 2t squared is going to be 4t squared. Careful, it's quantity 2t squared. And then 2 squared is going to be 4. Okay, so the arc length is going to be the integral from time 0 to 2 of this guy. Okay, here's the important bit. If you're taking the square root of something and you're integrating, really there are only two things that can happen that will allow us to calculate this. So number one, so it doesn't look immediately like we'd be able to do this because you would think, okay, we'd probably need to u sub or something like this. That's not an option because we don't have anything outside. We clearly don't have a u outside the square root with which to u sub. So what else could we do? Well, if it turns out that the square root of t to the fourth plus 4t squared plus 4 is a perfect square, then we could just actually take the square root of it and get rid of the square root entirely. Is there a way we can write t to the fourth plus 4t squared plus 4 as something squared? Is that a perfect square? So if instead, suppose it was t squared plus 4t plus 4, right? How would I write that? Not quite. On the right track, yes, right. So this is in fact t squared plus 2 squared. Right, when you FOIL that out, you get t to the 4 plus 4t squared plus 4. Right, we recognize t squared plus 4t plus 4 as just t plus 2 squared. But instead of t squared plus 4t, we have t to the 4 plus 4t squared. So we get a t squared plus 2 squared. Does everyone see that bit? This is something you're going to see a lot with these types of problems, because this is really one of the only ways these become feasible. Okay. So when we take the square root of the square, we just get t squared plus 2. So this is really the integral from 0 to 2 of t squared plus 2. That we can calculate. And so that becomes 1/3 t cubed plus 2t evaluated from 0 to 2. So that just becomes 8/3 plus 4, which we can simplify as 20/3. Okay, I already spent more time than I wanted to on that, but all of these arc length problems, either the magnitude r prime of t is either going to be a constant usually in the case of helices, or it's going to be a square root of a perfect square, in which case you can get rid of the square root. Basically 100% of these are going to be like that. So if you don't have a constant, try to write it as a perfect square. Or, okay, so sometimes we could pull out a t and do a u sub. But yeah, those are the minority. Okay. So that's the arc length formula, or the formula for arc length of a curve. Okay. So let's look more at arc length. So suppose we have a curve, once again, parameterized by r of t. T goes from A to B. And suppose We want to know how long, let's suppose this is R of A here. We want to know how far have we traveled from time A to some time t. Right? So at time A, we were here. At time t, we're here. How far have we traveled in that time? Well, we use the Arclength formula, right? We integrate from time A to time t of the magnitude of r prime. So integral from time A to time t, except now since we're using t in the integrands, and in the bounds of the integral, the thing we're integrating can't involve t, so we just have to call it something else. So let's just use u. There. So this is the Arclength formula, or basically, so S of t is how far have you traveled up to time t, right? So you plug in a time that tells you how far you traveled from time to that given time t.
Does this also work if you integrate from t to b?
So that's going to be a different thing. That's going to tell you how far. You can think of that as like how far you have left to travel until you get to the end. That, I mean, that's perfectly fine, but that's not going to be as useful for the things we're going to do in just a sec. But that is the thing you could integrate, but it would mean something a little different. Okay, so think of that as distance traveled until time t, right? So that's S of t. So what is the rate of change of distance, right? So you've traveled X amount of distance in X amount of time. What is the derivative of that? Ooh. Not quite, not quite. So velocity is the rate of change of position, right? And velocity has a direction. But this is just how far have you traveled? The rate of change. So the rate of change of distance with respect to time is just speed. So this is the distance you traveled up to time t. The rate of change is going to be speed. And from the fundamental theorem of calculus, that is just the magnitude r prime t. So speed at time t. So if that derivation didn't make total sense to you, or you have to think about it for a sec, that's okay. You don't need to remember that. You just need to remember speed is magnitude r prime t. Yes, so this integral is a scalar because we're integrating a scalar function. So since we're taking the magnitude of r prime t, that's going to be a scalar function rather than a vector. Okay. So remember, we talked last time r prime of t is a tangent vector so R of t gives us position. R prime of t. So suppose we're going in this direction along our curve. R prime of t, suppose this is r time t, is going to be a tangent vector. It's going to be, sorry, that is pointing in the wrong direction. It's going to be pointing in the direction of travel. So it's a tangent vector, tangent to your curve, pointing in the direction of travel. And the magnitude of r prime of t is the speed of travel. Well, basically, this is just the velocity vector. So if you think of r of t as position on your curve, r prime of t is going to give you the velocity vector. So that's going to give you the velocity, and then of a particle with position r of t. So r of t gives you position on your curve, r prime of t is velocity, magnitude r prime t is speed at time t. And we'll talk more about this when we get to motion in three-dimensional space, but it's useful to think about those, these in these terms. So for example, if r of t is t cubed negative e to the t 4t, find the speed at time 2. Find speed at t equals 2. So position is t cubed negative e to the t 4t. What's our speed at t equals 2? Well, the speed is the magnitude of r prime. So let's find r prime of t, then plug in t equals 2, and then take the magnitude, and then we'll be done. So r prime of t, taking derivative component by component. So t cubed becomes 3t squared, negative e to the t becomes negative e to the t. 4t becomes 4 when we take the derivative. So here's a little trick, or nice thing to remember. You could, so we need the magnitude r prime of t at t equals 2. So you could take the magnitude of r prime of t and then plug in t equals 2, but it's actually a little easier just to plug in t equals 2 now and then take the magnitude of that vector. Right, so r prime of 2, we get 3 times 2 squared is 3 times 4, which is 12. Negative e to the 2, 4. So the trick is anything that involves derivatives, after you've taken all of your derivatives, you can plug in a value of t at that point and then do whatever you need to do after that. If you've taken all your derivatives, you can go ahead and plug in your value of t and then do whatever you need to do after that. Okay, and so then the magnitude, our speed at time t equals 2, is the magnitude r prime of 2. So that's the square root of the sum of the component squares. So 12 squared plus negative e squared squared plus 4 squared. So 12 squared, 144. 4 squared is 16. So those are 160 together. And then negative e squared squared is just e to the 4. But it's simple. It's just a matter of remembering that speed is magnitude r prime t at time 2. Okay, and then finally, let's look at how to take a parameterization of a curve and change it into something more useful. So we're going to reparameterize our curve so that it has, our parameterization has specific qualities that we want. Okay, so I said a parameterization of a curve is just you have a vector function which traces out your curve as t varies, right? So you can think of it as just a way of traveling along your curve. So remember we said there are infinitely many parameterizations of a given curve, of one curve, because you can travel at different speeds. You can change speed, you can go the same speed, you can go one direction, you can go the other direction. You can be here at time t, and another could be here at that same time. There are infinitely many ways to travel along a curve, and those correspond to infinitely many parameterizations. So for example, suppose we had one curve given by parameterized by t squared t cubed. T goes from 1 to 2. And suppose we had a different parameterization. Let's use u, because remember, we can call a parameter for whatever we want. I'm just using t and u so we don't get them mixed up. So this is e to the u, e to the 2u, e to the 3u, and we're going to let u go from 0 to natural log 2. So you don't always have to include that, but for many of the curves we'll deal with, we do. It's because usually if you don't say t goes from, say, a to b, then we're assuming t goes from negative infinity to positive infinity. And that gives you some usually infinitely long curve in space. But if we only want to consider a piece of this, we say t goes from 1 to 2. Then we get the piece of the curve which goes from time A right here to time B here. So we're only considering this little piece of the curve. So usually if you don't specify that, then we can't talk about arc length of a curve because it could be infinitely long. Yeah. Okay. So these two actually describe exactly the same curve. Even though they don't really look very similar. So notice we just let, if you replace t with e to the u, you get e to the u e to the u squared, which is e to the 2u, and e to the u cubed, which is e to the 3u. And since t goes from 1 to 2, we want e to the u to go from 1 to 2, right? And so e to the 0 is 1, e to the natural log 2 is 2. And so we're going to go, it's going to parameterize exactly the same curve, except it's just two different ways of going along the same curve, basically. They're going to represent like going at different velocities at different times, et cetera, along the same curve. But what you're doing is you're just replacing with t with e to the u, and you see you get exactly the same curve in this case. So these are just two different parameterizations of the same curve. So one way you can get a different parameterization, so the way you can get a different parameterization is, so suppose you have a curve parameterized by r of t. So you can let t you can replace t with a function of u, right? And so essentially what you're doing is you're reparameterizing the curve by letting t be a function of something else. And so here's what that kind of looks like. So we're going to let u go from c to d. So here's our initial parameterization. Okay, so parameterization is really just a function from t into the vectors, and that's going to trace out some space curve. Instead, what we're going to do is we're going to have another function from sort of the real numbers to the real numbers. So from u to this guy, that's going to be g. And we're going to let a new parameterization using u. It's just going to be the original guy of g of u. So for instance, in this case, what we did was, suppose we started off with this guy here. We could reparameterize by saying, okay, let t be e to the u. And then our R2 of u is really just the first guy, but instead of t, you plug in e to the u. That's a reparameterization. I don't want to dwell too long on that, but that's sort of how these reparameterizations are going to work. And in particular, there are specific reparameterizations that are really useful for certain things. So one really useful way to parameterize your curve is an arc length reparameterization, right? So we're going to parameterize our curve so that we basically start at one end at time 0. We move at constant unit speed at speed 1. So we're going to parameterize with respect to arc length. So we'll call it S here for our arc length parameterization of a curve. So in other words, the speed is always for all times on here, we're always going a constant unit speed along our curve. That's going to be a useful thing to tell us something geometrically about our curve. Some things. Another thing about arc length reparameterization is that at time s, you've traveled exactly distance s along curve. So you're going to start at one end at time 0. And then if you give a time s, that's how far along the curve you traveled. And it makes sense because you're going at unit speed. But you just shift your time so that you start at one end at time 0. And then at time s, you've traveled along exactly distance s along your curve. So this is going to be a useful thing to have. We'll see that in practice, we don't actually calculate it. And then actually sometimes usually it's impossible to actually calculate. But we'll give some curves, and then we'll show how to actually reparameterize the curves so that you have the arc length parameterization, right? So you're going unit speed along your curve, and at time s, you've gone exactly distance s along your curve. So how to reparameterize with respect to, so WRT is going to be with respect to, I'll use that every so often, with respect to arc length. So if we have a parameterization, how do we change it to an arc length parameterization? So first thing to note, we're given a parameterization R of t. We need to make sure this only works if the parameterization, R prime of t is never the 0 vector. This is only going to work then. So step 1, we're going to find the arc length function. So remember, that's going to be the integral. It's going to go from time 0 to time t now, instead of from time a to t. So s of t is going to be the integral from 0 to t, magnitude r prime u du. And we're using u in the integrand just because we're using t in the bounds of the integral, so that the integral makes sense. So this is, let me write it this way. So the arc length s is going to be some function of t. So we're going to find the inverse . So we find the arc length function, and then we find the inverse of that, right? So we have s is equal to some function of t. Then we're going to get t by itself and write it as some function of s. And note, this is possible. This is why we need r prime t to be non-zero. Some technical stuff, but it means that magnitude r prime t is never 0, and so that this guy is an increasing function. And so it's always going to have an inverse, but don't worry too much about that. And then our arc length parameterization. So our parameterization of our curve with respect to arc length is just going to be your original parameterization, but you replace t with g inverse of s. Okay, so we do this integral. That's going to give us a function of t. So we have s is equal to some function of t. And then we find the inverse so that we get t is equal to some function of s. And then you go to your original parameterization, you replace t with that function of s. And that is going to give you the arc length reparameterization of your curve. So let me say this is usually impossible to do explicitly because this guy often does not have a very nice inverse. So we usually just have to give very simple examples. But one such nice example are helices. Suppose we have the helix given by cos 4t, sine 4t, 3t. So let's find the arc length parameterization of this curve. Okay, so we're going to go step by step. Number one, we need to get the arc length function. So s is going to be equal to the integral from 0 to t of the magnitude r prime u du. So really quickly, so r prime t is going to be -4 sine 4t 4 cos 4t 3. And so then magnitude r prime t is going to be the square root of 16 sine squared 4t plus 16 cos squared 4t. So that's going to be 16. 16 sine squared plus cos squared plus 3 squared, which is 9. So root 25, which is just 5. And so magnitude r prime u, you're just replacing t with u, but there is no u. So we're just integrating 5 from 0 to t. And that is just writing it out, u equals 0 up to t. That is just 5t. Did I plug in 1 for t? Where? Exactly.
I don't know where you got the 16 from, and the 16 plus 9 in the inside.
So I took the when you take the magnitude, so that's the square of this plus the square of this plus the square of this. This is 16 sine squared 4t. This is 16 cos squared 4t. So 16 sine squared plus cos squared. Doesn't matter the 4t, they're the same thing. That sine squared plus cos squared is 1. And so we
Gotcha.
yeah.
All right, thank you.
Okay, so we have s is equal to 5t. This is a particularly easy function to find an inverse of. S equals 5t. So we want to write t as a function of s. Well, you just divide both sides by t, or by 5 to get t by itself. T is s over 5. And so that's our G inverse of S. We wrote T as a function of S. Now that's going to be, we go to original parameterization. Our Arclength parameterization is just going to be our original guy but you replace T with S over 5. How did you get 5 again? Because R prime of T was this guy, magnitude R prime of T. When we take the magnitude, you get square root of 16 from the sine squared and the cos squared plus 9. 16 plus 9 is 25. Square root of 25 is 5. Sorry, I'm going through this a little quickly because I'm very into class, but does that answer your question? Okay. So our arc length parameterization, go back to the original parameterization and just replace T with S over 5. So we get cosine of 4 times S over 5. Love how my S's and 5s look exactly the same. Sine of 4 S over 5. My God, it's even more similar. Shoot me. And then 3t becomes 3 times S over 5. And that is our arc length reparameterization. If you want, you can check that the magnitude of this is always 1. I won't do that here. But that means we're always going unit speed along our curve, which is what we want. Okay, any questions? Alrighty, then that is it for this chapter. So we will talk about 13.4 next class, and I will see you then. Have a good rest of your day, and I will see you tomorrow.
Thank you.